Hello folks. For the lesson today, we're going to start by recapping Kirchhoff's law, and we're going to do that by looking at a few examples out of the textbook just to warm us up here. So Kirchhoff's laws, there's two of them. The first one is the voltage law, which states that around any complete path through an electric circuit, the sum of all of the increases in electric potential is going to be equal to the sum of all the decreases in electric potential. So an example of that would be this first question. You can see the page number here from your textbook. We are looking for the total voltage in the circuit here. We can see that there is a voltage drop of 12 volts through this resistor, a voltage drop of 18 volts through this resistor, and a voltage drop of 20 volts through this resistor. So along any complete path, which you can draw the circle of the complete path here. You don't have to do that, you can visualize that, but that's the path that the electrons are taking in that circuit. All of those drops have to add up to the potential increase through the actual battery here. So in other words, we can say that V0 is equal to V1 plus V2 plus V3. And if that's the case, we just add up all of the resistances, all the voltages through the resistances. So 12 plus 18 plus 20. That's going to give us 30 plus 20, which is 50 volts. So that's Kirchhoff's voltage law. If we look at this example here, Kirchhoff's current law states that at any junction point in an electric circuit, the total electric current into the junction is equal to the total electric current out of the junction. So that means junctions, by the way, are spots where the circuit will break up into different paths. So you can consider this as a junction, you can consider this as a junction. You can see that we are looking for the total current. Now remember, one way to visualize this is that current, remember, is just a number of electrons going through the circuit point, at this point in the circuit, over a certain amount of time. So you can't add or subtract electrons. The same number of electrons that are passing through one point has to equal the same number of electrons going through another point, but they split up at a junction. So we can see that there's 2 amps in this branch here. There's 1 amp in this branch here, and there's 4 amps in this branch here. Well, those are all going to add together. Amps are just a number of electrons, basically. So we're just going to add up all of those together to find what the total current is. So we would write that I0 is equal to I1 plus I2 plus I3, and that gives us 2 amps plus 1 amp plus 4 amps. 3 plus 4 is 7 amps in total. So that's basically how Kirchhoff's voltage and current law works. Now, before I move on to the next example, the voltage law still works here, but there are multiple circuits. So if we knew the voltage going through this battery, let's say it was, let's say it was 12 volts, okay? Through a circuit. Well, how could I draw the circuits here? Well, my first circuit I could draw going through this branch. It's not quite of a circle in this case, but it is a circuit. Okay, that's the path that the electrons would take. The voltage that you gain in the battery has to be lost in the resistor. Well, if you gain 12 volts, you got to lose 12 volts in this scenario. In the next circuit, which would be this one, same thing happens. You gain 12 volts, you lose 12 volts. And the last circuit, which would be this one, once again, you gain 12 volts, you lose 12 volts. So these 3 resistors, if you remember, are called resistors in parallel. They all have the exact same voltage as the battery. So they're stealing the 12 volts from the battery as the electrons go through. And each one of them has the exact same drop in potential. Okay, so you're gaining 12 volts, you're losing 12 volts. You're gaining 12 volts, you're losing 12 volts. So that's how a parallel circuit works. In this case here, the voltages all added up to give the total voltage. This is a series circuit. The current would actually be the same. So if you had 5 amps of current going through this circuit, you would have 5 amps of current all the way through in any position. And that's also a part of Kirchhoff's laws. So question number 3, and this is out of the textbook, says calculate the total electric potential difference across 3 6-volt batteries connected A in series and B in parallel. So this time it's talking about the batteries that are connected in series and the batteries that are connected in parallel. I just put a resistor here just to have a circuit that's not going to catch on fire, because if you don't have any kind of resistance in a circuit, you can easily short circuit and cause a fire. But we're talking about what is the rise in potential here, and what is the potential on each one here. And you'll see that a voltmeter usually is drawn as a circle connecting to both sides of the either the load, or in this case the increase in potential that you're trying to measure. Now what you would see here is, if you think of the electrons going through this 6-volt battery, they've now gained 6 volts of energy. Joules per coulomb is volts, so they're gaining 6 volts of energy, another 6 volts of energy, another 6 volts of energy on top of each other. We would add those 3 together to get your 18 volts. Okay, so across all 3 of them added together, you just add the voltages together. Very similarly that we did with the resistors above. For a parallel circuit, if you're measuring 6 volts on this battery, as long as all the, these are cells, by the way, because they're individual parts of a battery, but if they're all 6-volt cells, you're going to measure 6 volts no matter where you are. So even if you measure it what kind of looks like the total for the entire circuit, you're, as well as for this cell alone, it doesn't matter. All 3 of them are just going to give 6 volts. Now the benefit to having power in parallel like this is, if one of the batteries dies, you're still going to be giving energy to this resistor, because the other 2 cells are still going to be working. Okay, whereas if this cell dies, you're actually breaking the connection, and there's no more electricity flowing to this resistor. Okay, because the electrons can't get through here. So if you think of a household circuit where you have plugs along your wall, if you unplug something, the other things that are connected on that circuit are still going to be working. So in a house, usually circuits are parallel along like a series of lights or plugs. But a house wiring system is a little bit different, because it's actually a combination, which we haven't seen yet, but it's a combination of both series and parallel circuits, because you have a breaker that is going to be connected in series with the circuit that is connected in parallel. And if there's a problem with one of the plugs overheating or something like that, the breaker is going to cut the power to the entire circuit. So that kind of represents a series scenario. If one thing goes out, like a breaker, if that disconnects a whole bunch of things that are connected in different plugs, then that's a series scenario. But if the circuit is working fine and you unplug a light, it's not all the lights that go out. Okay, so for a household, it's a little bit complicated. We'll look at that a little bit more in detail later. But generally speaking, most of your circuits in your house are parallel circuits. Looking at number 4, a little bit more complex picture here, and this is actually a scenario where we have a series resistor, we have some parallel resistors, and they're asking us to fill in all of that information. Now, I find sometimes when I have a more complex circuit like this that it helps me to organize things in a table. I'll put V and I, and we're only looking for V and I here. If we were talking about R, the resistance, we could put a third column here, okay? But we're just looking at the voltage and the current. And I listed the subscripts of each one of these in this column. So this would be V0, which is your 18 volts right here. Okay, V1, V2, V3, V4, and you can see which ones are missing, right? Anything that has a question mark is going to be missing in the table. So I just find it helps me organize my thoughts and to see what do I need to find and which ones are missing, which ones I haven't found yet. Okay, so if we take a look at this, I mean, there's multiple ways that we can start, but I think what I would start with is this junction right here, because we can see that there's 3 amps going this way, and one of the values that we're looking for is this current here, which we don't know, but we do know that the amount of current coming in was 4 amps. And we know that at a junction, that 4 amps has to split up into 2 currents that are going to add up to give whatever that current was. So if I'm getting 3 amps this way and it was 4 amps coming in, I3 has to be 1 amp. So if I go down to my table here, I can go to the I3 and put a 1 here and see that 1 plus 3 is equal to 4, because that is Kirchhoff's current law at that junction. If we now look at this voltage here, so we could draw, oh, by the way, I should probably do this at the same time, actually. Let's get all the currents done. I'm just looking. Again, you can do this in any order you want, but I was just looking down here at the I4. Well, this is the other current that's joining to I4. I'm hoping everybody can understand that if you have 4 amps coming in, it breaks up into 3 and 1, and then when it comes back together, it's going to be 4 again. So that's pretty easy to fill in I4 as well. So let's just put 4 amps there. Okay. For the voltage, as I was explaining a couple seconds ago, if we look at Kirchhoff's voltage law, if I have 6 volts here, right, and coming down this direction, I have 3 volts here that I've taken away. And by the way, it was 18 volts to start. Okay, so the 18 volts to start, we have 6 volts taken away here, we have 3 volts taken away here. That's a total of 9 volts. How many volts are left to go through voltage 4? So we could write the equation out, but I'm sure you can see that the answer is going to be 9. So let's just fill that in. So again, through this red circuit or path, we have 18 volts being given to the electrons, 6 volts being taken away, 3 volts being taken away. That's a total of 9 volts being taken away. So V4 has to be 9 volts. We can also see a couple of things here. These 2 voltages are parallel to each other. That means those 2 voltages have to equal one another. Well, if we now know that this one's 9 volts, another way that we can do that is by doing another path. If we do the path going this way through the circuit, so again, 18 volts are being given, 6 volts are taken away, 9 volts are taken away. That's a total of 15 volts out of the 18, so the V2 has to be 3. So there's a couple of ways of figuring out V2 here. You can just look at them as being parallel, and all parallel voltages will be the same. Or you can do the Kirchhoff's law to find out that that's going to be 3 volts as well for voltage 2. And well, I just realized there's no I0 that is being asked in this picture, unless I forgot to draw it. No, there's no I0 being asked to draw, but I0 and I4 are going to be the same as I1, because if you look at how the circuit is drawn here, I0 would be right here. So what is the total amount of electrons going through the battery, basically? Well, that has to match the total amount of electrons in this path here, which is counted as 4 amps. So we know that this is actually 4 amps as well. So I like the table. It helps me organize things, and when we get into more complex resistances in parallel and series later, This will kind of help organize that. Now, in your lab, you also recently figured out that V is equal to Ri, or R is equal to V over I. Well, now that we have the V and the I here, we could actually divide those two numbers. And like I said, we could have a third column, or a fourth column, I guess, for resistance here. And we could actually use this equation to calculate what are all of those resistances, because we just divide all of these numbers. Okay? And we'll talk about that a little bit more, because we're going to be soon dealing with Ohm's Law. So question number 6, draw a circuit diagram that includes an electric motor, a green light, a red light, and a switch. If the motor is on, the red light must also be on to warn people of possible danger. If the motor is off, the green light should be also on. Now, it's a little bit misleading in this question, because the green light basically is going to be on no matter what. They didn't suggest that the green light is turning off. That's kind of just to throw you off the path. This is the circuit that I drew to represent this. I went and found the symbol for a motor, which is just a circle with an M in it. And as you can see, this cell here is producing energy through this path here, going through the green light. And that means the green light's going to be basically constantly on. But they wanted the switch to control when the motor is on, that the light that's red also comes on at the same time. So this is the symbol for a switch. When a switch is closed, it goes across like this and completes the circuit branch. But you can see that as if I press the switch down, both the motor and the light would turn on, but the green light would also stay on. If the green light had to turn off when the motor was switched on, that would be a whole different story, and we'd probably need another switch for that. But for right now, this is one picture. I mean, the motor and the light could have been on this side instead, but this is one of the pictures that I figured would complete the instructions of the question. Okay, so let's talk about what resistance is. Resistance is the opposition to the electron flow due to a load using up the energy which is given to the atoms or molecules of the conductor. So, oh, I spelled molecules wrong here. So basically, you need resistance in a circuit, or else you're going to have a short circuit. Now, let's talk about if you've ever seen an electric stove as an example. An electric stove has a coil of a material that heats up when electricity passes through it. Well, what is happening there? That coil has a high resistance. So as the electrons try to get through, they're going to encounter the molecules inside of that material, giving those molecules their energy, therefore heating them up. And we're going to talk about what factors influence resistance. So why is that material going to heat up more than potentially another material that's also getting electricity passed through it? But that's basically how resistance works. By the way, if you need to pause the video at any time to write stuff down, please feel free to do so. If you weren't doing it during the homework correction, or the examples that what I was showing, I should say, you can go back and look at those and write them down, but you should definitely be either taking some notes now or doing it later, whatever you prefer to do. Now, what are the four factors that influence resistance? So one of them is resistance is proportional to length. So hopefully you remember this proportionality symbol here. Basically, that just means that if the length increases, the resistance also increases. If the length decreases, resistance decreases. So I hope that makes sense, that the longer the wire is, the more molecules that the electrons have to get through. Therefore, it's going to be harder and harder for them to get through the longer and longer the wire is. The area of the transverse section is also going to affect the resistance. So basically, the wider the wire, the less resistance there are, and the narrower the wire, the more resistance there is. So the resistance is proportional to 1 over the area. As the area increases, the resistance decreases. As the area decreases, the resistance increases. So that's an inverse proportionality. We've talked about inverse proportionalities before. By the way, if we were to graph resistance versus length, it would give us a straight line. If we were to graph resistance versus area, it would give us a curve going down like this. So that's another way of visualizing it, right? As the length increases, the resistance increases. But in this case, as the length increases, as the area increases, the resistance decreases. And it's not a linear relationship. The type of material. So if you have really good conductors, your resistance is going to be low. If you have really bad conductors, the resistance is going to be high. Sometimes you want high resistance because on a stove, the material that's used there is generating heat, and we want a lot of heat when we're heating up our food. So we want a bad conductor there, which means we're going to have to force those electrons through with a lot higher of a voltage. But that's to produce that heat. Okay. Your clothes dryer, if you have an electric clothes dryer, has an element inside that also heats up with electricity. So it's the same idea. It's a bad conductor in order to increase the resistance so that the heat that's produced is as high as it needs to be to heat whatever it's heating. But good conductors, one of the best conductors out there is gold. Gold is used in a lot of computer parts to increase the conductivity so that the electrons flow with the least amount of resistance. In a computer, heat is bad because, as you're going to see in the next thing, as the temperature goes up, your resistance usually increases as well. And that's because inside the material, your molecules are moving faster and faster and faster, and it's a lot harder to pass an electron through molecules that are vibrating fast than it is to pass electrons through molecules that are vibrating slow. Which brings up the idea of superconductors. At around negative 270 degrees Celsius, your resistance for some materials is almost zero. And we've talked, I think, briefly about maglev trains before, but there are trains that are being built. Japan was one of the forerunners of this, where this is the train car here. And the train car, and I'm exaggerating how much of a distance this is, but you've got a North Pole magnet and a North Pole magnet on the bottom of the car, and they use superconductivity to make these magnets as powerful as they possibly can be, so that a north and a north, as you probably know, and we will be discussing this when we get into magnetism, repel each other. So the train actually floats above the rail, therefore reducing the resistance between a normal train would have wheels contacting the rail, which increases the resistance enormously. So this really reduces the amount of energy that's required to propel the train. And what they'll do is they'll also put a North Pole angled with the rail, so you'll also get propulsion. And what they do is they don't leave the rails on all the time. They pulse the electricity, so the train is only supported where it is in that period of time on the rail. So it leaves the it leaves the station. The magnets under the train at the station are on. As it moves forward, the magnets at the station are turned off, the magnets under the train are turned on, and because you have the magnets just behind the train on all the time, it's pushing the train forward. So you don't even need an engine on this train, which makes the train a lot lighter and easier to push. Now, the idea of temperature is a little bit strange when you come to semiconductors, which we're not going to talk about too much, but there are materials that have been discovered where the resistance drops a little as the temperature increases, and semiconductors are used a lot in electronics because of this reason. So during the lab, you were doing some experiments with resistors, and I just wanted to talk about the color bands on the resistors and how to read them temporarily here. This is more an interest thing. Some of you may end up working with electronics, or maybe you already do. But how do you read the color codes on the resistors? So I've posted this handout in the Google Classroom that basically explains how it works. And I'm also going to call up the resistors from the lab here to talk about it. So I'll just show you what I mean. Now, this resistance goes up by 0.5. It doesn't change at the 0.5s. So if I go to 10.5, there's no change there. Oh, sorry, it is a change. Okay, I'm surprised at that. But usually it changes only on the whole numbers. So between 12.5 and 13, there's no change. See that? That's what I meant. Okay. So you don't usually have the decimal values here, but you can see that the color bands do change as the resistance changes. Okay. So so why is that? Well, why is it red and green and black when we're talking about 25 ohms? Now you'll notice that this band here didn't change in color at all. And here's the reason why. The first band is the first digit of your number of resistance. You'll look down here. Each color has a number associated to it, okay? And you'll notice that these two columns are exactly the same. So black always represents 0, brown always represents 1, red always represents 2, etc., etc. There are mnemonic sentences that help you remember what the order is here. I'm not going to tell you what they are because there's very many of them, but if you look up on Wikipedia for color code sentences, you'll probably find one pretty easy for resistors. Okay, so if we're looking at what color is, or what number is red, red is 2. So if you look at here, because I've got a 25 ohm resistor, the first band is going to be red because red represents 2. The second band is green. If we go back to the resistance here, green is 5. So if we're looking at the second color, that's the second figure or the second digit in our number, 25 would be red and green. The third number is the multiplier. So this is scientific notation, okay? So it's times 10 to the power of something. Well, 25 is times 10 to the power of 0 because it's just 25. 10 to the power of 0 is 1. So the band is going to be black because that's going to represent that it's a power of 0, okay? The last color is what's called the tolerance color. You have resistances that are better than others based on their construction. The less good ones are cheaper. So that's what the last band tells you. If you have a gold band, it's plus or minus 5%. A silver band is plus or minus 10%, which is actually a worse resistor. So if you don't need it for very, very specific things, if it doesn't have to be a perfect resistance or as close to perfect as possible, you can buy a cheaper one that's going to have a silver band there. And if it has no color, which is possible, there wouldn't be a fourth band, then it represents 20% plus or minus. Okay, so that's called the tolerance band. So usually the first 3 bands are the only ones you need to look at. So I want to show you that the third band, which is the multiplier, will change in color as you get up into higher resistances. So if I go up into the hundreds here, boom, you'll notice that that band changed colors now. Okay, that third band represents times 10 to the 1 now because brown is 1. Okay, times 10 to the 1, you're going to get into, with 2 digits, times 10 to the 1, it's going to be in the hundreds. So I just wanted to briefly discuss that because you probably saw it during the lab. And if you're interested in it, you can do a little bit more research if you ever need to know what the different colors mean. The last thing I'd like to talk about today is Ohm's Law. This was also something that you were kind of investigating during the lab that we did. Ohm's Law is named after, his name is Georg Simon Ohm. And if you look at his lifespan here, this is still quite a long time ago. So these were giants in science if we're still using a lot of their laws. Basically, we've already talked about this, that resistance is equal to voltage over current. Now, the thing is, we used what are called ohmic resistors in the lab. And I had talked about this a little bit in class in the sense that if you try to do the lab that we did in real life, it's very, very difficult to get reliable information. And students have often gotten hurt because if you wire a circuit wrong, you can heat up a resistor or you can short circuit the circuit and you can cause burns and stuff. So doing it digitally is quite nice with the circuit app that we used because you get perfect answers. But in reality, it's very difficult to get those perfect answers. So that's another benefit of doing it digitally. If you have a non-ohmic resistor, so let's say we had done the experiment with a light bulb, you can't guarantee that a light bulb is actually going to give you the right answers because you're supposed to get a straight line when you do voltage over current. And with light bulbs, you'll often get a curve. As the voltage increases, the heat in the light bulb causes the current to not flow the same way anymore, which we talked about earlier, right? Temperature changes resistance. So you'll get this curved effect here, which will change your answers in your lab, and then your numbers don't make sense too much anymore. So there's a difference between ohmic and non-ohmic resistors. We basically stick to ohmic in grade 11 and mostly through university as well. And what we discovered is the equation that relates voltage, resistance, and current is V is equal to Ri. So what this means is your resistance is usually a set number. So let's say your resistance was 10. If your current has to be 2 times 10 is 20, your voltage would have to be 20 volts to allow current to pass through that resistor. Now it could be higher, okay, but the minimum would have to be that number. So if your resistance is set and your voltage increases, your current is also going to increase, which means voltage is proportional to current, okay? Or current is proportional to voltage, I should say. So that is the equation that relates those values together. So I'm going to leave you some work out of your textbook here. I'll post this to the Google Classroom as well. If you can work on using this equation during those questions, that would be great. If you have any questions, please let me know, and we will talk to you soon.